When you have large optical thickness, it means radiation has to penetrate longer and along the way gets absorbed as well. In such cases, to get better and sensible results, we need to have the complete effect of radiation modeling, which should be included in the energy modeling as well. In order to couple the energy and radiation intensity equations at each cell, solving them simultaneously will enable the DO energy coupling. This approach accelerates the convergence of finite volume scheme for radiative heat transfer and can be used with gray or non-gray radiation model. The setting is done here when we activate the DO energy coupling, which is solving the energy equation and the DO equation simultaneously. If you are using the non-gray P1 model or the non-gray DO model, you can specify a different constant. Now we will come to radiation properties. If you are using a non-gray P1 model or non-gray DO model, you can specify a different constant absorption coefficient for each of the band used by the gray band model. If you are using the non-gray P1 model or the non-gray DO model, you can also specify a different constant refractive index for each of the bands used by the gray model. After this, let us discuss the boundary conditions required for setting up a radiation model. When radiation is active, you can define the emissivity at each inlet and exit boundary condition. This is done when you are defining boundary conditions in the associated inlet or exit boundary dialog box, like the pressure inlet dialog box, the velocity inlet dialog box, pressure outlet dialog box, and many other boundary conditions. Enter the appropriate value for internal emissivity, which appears here when the radiation model is active. Select the specified external temperature in the external black body temperature method drop down list, and then enter the value of radiation boundary temperature as the black body temperature. When the S2S model is used, you can specify that some of the walls and inlet as well as exit boundaries are not participating in view factor calculations. This capability allows you to save time computing the view factors and also reduces the memory required to store the view factor file during the ANSYS fluent calculation. In the radiation tab of the wall dialog box, we have to select opaque in the boundary condition type drop down list to specify an opaque wall. So this is the selection where we select opaque boundary type. This is applicable for the DO model. Opaque walls are treated as gray if gray radiation is being computed, or non-gray if the non-gray DO model is used. If the non-gray DO model is used, the diffuse fraction can be specified for each band. This is where we specify the diffuse fraction. After you have selected opaque as the boundary condition type, you can specify the fraction of reflected radiation flux that is to be treated as diffused. By default, the diffuse fraction is set to 1, indicating that all the radiation is diffuse. A diffuse fraction equal to 0 indicates purely specular reflected radiation. A diffuse fraction between 0 and 1 will result in partially diffuse and partially specular reflected energy. To define radiation for an exterior semi-transparent wall, click the radiation tab in the wall dialog box and then select semi-transparent as the boundary condition type in the drop-down list. That is, in any wall boundary condition, we select boundary condition type as semi-transparent. Now we will discuss the solid cell zone conditions for the DO model. With the DO model, you can specify whether or not you want to solve radiation in each cell zone in the domain. So when you open the dialog box for that particular cell volume, you have an option which says participates in radiation. You can select or you can avoid to select it. You can specify whether or not you want to solve radiation for each cell in the domain. By default, the DO equations are solved in all fluid zones, but not in any solid zone. If you want to model semi-transparent media, for example, you can enable the radiation in solid zone. To do so, enable the participate in radiation option in the solid dialog box. Before we end this particular session on radiation modeling, let us discuss what all results can we extract from a radiation analysis conducted in ANSYS Fluent. We will shortly see the list. If you want to try out more, you can certainly take up a radiation modeling sample case and try out what all results you can extract. In the radiation category, we have the incident radiation, which is there for P1 and DO model. These results can appear in the form of contour, plots, vectors, and reports. In the radiation category, we have the incident radiation, which is there for P1 and DO model. Incident radiation for different bands, which is there for non-gray P1 and non-gray DO model. Absorption coefficient, which is there for DTRM, P1, DO, and Rosen models. Scattering coefficient, which is there for P1, DO, and Rosen models. Refractive index for P1, DO, and Rosen models. Radiation temperature, which is there for P1 and DO model. Surface cluster ID, which is there for S2S model. If you want to go to wall fluxes category, we have radiation wall flux for all radiation models, surface incident radiation for the S2S, DTRM, and DO model, absorbed radiation flux for the DO model and semi-transparent walls, reflected radiation flux for DO model, semi-transparent walls, transmitted radiation flux for DO model and semi-transparent wall, beam irradiation flux, which is there for DO model and semi-transparent walls. For reporting radiative heat transfer flux through boundaries, there are different options. For that, we have to go to report fluxes and setup. Overall heat balance we can check when we are using DTRM model. You can also display rays and clusters for DTRM. And the displaying cluster we have already seen. So these are the different results that are visualization options which we have for radiation modeling. So to summarize this particular session on radiation modeling in ANSYS Fluent, we have revised the fundamental concepts of radiation within this session. Also, we discussed the basic equations and theory behind modeling radiation. We saw application of radiation modeling in Fluent. We also discussed 4 radiation models, that is P1, DTRM, S2S, and DO, from the conceptual as well as setup point of view. We also discussed different material inputs, boundary condition inputs, when we use radiation models, and what are the different visualization or result options which can be extracted within a radiation problem. So thank you for attending this particular session. This will be the last lecture in the heat transfer modeling advanced heat transfer course offered by LearnCX. If you have any queries regarding this course on any material of the course, feel free to email us at info@learncx.com. Thank you.